Euclid's Elements, Book 3, Proposition 13. A circle does not touch another circle at points more than one, whether it touches internally or externally. So let's have a circle, and let's have another circle touching more than once. And remember, Euclid defines touching as circles that meet but don't cut. So we want another circle that touches this circle more than once internally. And so we can draw it something like this. And then we want another circle that touches externally. It's going to look something like that. And they're going to look a little weird, but that's not why we reject them. We're going to reject them not because they look weird, but because there is a logical contradiction. So let's have our initial circle. We'll call this A, B, C, and D. So our black circle is circle ABC, and we have an internal circle. Let's call that circle FCD. So it's given that circle FCD touches circle ABC more than once, so at least twice. And we also have circle, let's call this AB, let's call this one ABE. So we have circle ABE that touches circle ABC, again, more than once. We're going to show that this is impossible. So the first thing let's do is take the center of circle ABC. So we know we can take the center of any circle. That's prop 1 of book 3. And so let's have the center of circle ABC. So let's have the center of ABC, circle ABC. Let it be G here. And let's have the circle. Let's have the center of circle FDC, and let's have that be point H. And we put these, and again, these are going to look a little odd, but that's not why we reject them. All right, and we know from Book 3, Prop 11, that if a circle touches another circle internally and we join the centers, when we join the centers and continue them, they will touch the points of contact. So they're going to touch this on both sides where these circles touch one another. So now let's look at this circle, this black circle. So we know that if this is the center, we know that GD is equal to GC because those are radii of the same circle. And if GD is equal to GC, then it's certainly, if we remove, so let's remove GH from GC, right? Then the remainder, GD, has to be greater than the remainder, which is HC. And then if we added that back, if we added GH back to this side, well, then what remained there, DH, would be much, much greater than HC. So let's hold on to that for a second. That's what we get by looking at the black circle. But in the blue circle, right, H is the center. So if H is the center, then we have DH is a radius, and HC is a radius. And we know the radii are equal. Therefore, DH is equal to HC. But wait a minute, we just proved that DH was much, much greater than AC, and now we're saying that it's also equal? It can't both be equal to and then also much greater than at the same time. So this is an absurdity, and what gave rise to this absurdity is assuming that we could have a circle touching another circle more than once inside. So internally, this leads to a contradiction, and it doesn't work. We're going to see that there's another contradiction when we try to see if it can touch more than once externally. So let's join points A and B and try to join those here in a way. And we know from when we join 2 points on a circle, we know from Proposition 3, Book 2, that if we join any 2 points on a circle, it falls inside the circle. Therefore, AB falls inside both circles. It falls inside circle ABC, but it also, by this prop, has to fall inside circle ABE. Well, it's inside circle ABC, but look, it's outside. It's completely outside circle ABC. And it can't always be inside a circle, but also outside. So that is a contradiction. It's supposed to be inside both circles, but it's clearly outside the smaller circle. So that leads us to reject this possibility, that it can't touch externally on the outside. This was ABC, this was ABE. So the blue circle can't touch twice internally, it can't touch twice externally. Therefore, if 2 circles touch one another, whether internally or externally, they do not do so in more than 1 point. And since that's what we were given to prove, we can now conclude QED.